Now let's have a look how the connection establishment occurs. To establish a connection, TCP uses a three-way handshake. Before a client attempts to connect with the server must first bind to and listen at the port to open it up for connections. This is called a passive open. Once the passive open is established, a client may initiate an active open. To establish a connection, the three-way handshake occurs. First step is the SYN. The active open is performed by the client sending a SYN to the server. The client sets the segment sequence number to a random value A. SYN Ack is the second step. In response, the server replies with a SYN Ack. The acknowledgement number is set to one more than the received sequence number, A+1, and the sequence number that the server chooses for the packet is another random number, B. Step 3. Acknowledge Ack. Finally, the client sends an Ack back to server. The sequence number is set to the received acknowledgement value. For example, A+1, and the acknowledgement number is set to one more than the received sequence number, B+1. At this point, both the client and server have received an acknowledgement of the connection. The steps first and second establish the connection parameter for one direction and it is acknowledged. Steps 2 and 3 establish the connection parameter for the other direction and it is acknowledged. With this, a full duplex connection is established. Now let's have a look how connection termination happens. The connection termination phase uses a four-way handshake with each side of the connection terminating independently. When an endpoint wishes to stop its half of the connection, it transmits a FIN packet which the other end acknowledged with an ACK. Therefore, a typical teardown requires a pair of FIN and ACK segments from each TCP endpoint. After both FIN-ACK exchanges are concluded, the side which sent the first FIN before receiving one waits for a timeout before finally closing the connection, during which the time the local port is unavailable for new connections. This prevents confusion due to delayed packets being delivered during subsequent connections. A connection can be half open, in which case one side has terminated its end, but the other has not. The side that has terminated can no longer send any data into the connection, but the other side can. The terminating side should continue reading the data until the other side terminates as well. It is also possible to terminate the connection by a three-way handshake when host A sends a FIN and host B replies with an fin and ACK, and host A replies with an ACK. This is perhaps the most common method. It is possible for both hosts to send fins simultaneously, when then both just have to ACK. This could possibly be considered a two-way handshake, since the fin ACK sequence is done in parallel for both directions. Some host TCP stacks may implement a half duplex close sequence, as Linux or HPUX do. If such a host actively closes a connection but still has not read all the incoming data the stack already received from the link, this host sends a RST instead of a fin. This allows a TCP application to be sure the remote application has read all the data the former sent, waiting the fin from the remote side when it is actively closed the connection. However, the remote TCP stack cannot distinguish between a connection aborting RST and this data loss RST. Both cause the remote stack to throw away all the data it received, but that the application still didn't read. Some application protocols may violate the OSI model layers using the TCP open-close handshaking for the application protocol open-close handshaking. This may find the RST problem on active close. Most implementations allocate an entry in a table that maps a section to a running operating process. Because TCP packets do not include a session identifier, both endpoints identify the session using the client's address and port. Whenever a packet is received, the TCP implementation must perform a lookup on this table to find the destination process. The number of sessions in the server side is limited only by memory and can grow as new connections arrive. But the client must allocate a random port before sending a first SYN to the server. This port remains allocated during the whole conversation and effectively limits the number of outgoing connections from each of the client's IP addresses. If an application fails to properly close unrequired connections, a client can run out of resources and become unable to establish new TCP connections, even from other applications. Both endpoints must also allocate space for acknowledged packets and received data. There are few key features that set TCP apart from UDP or User Datagram Protocol. Ordered data transfer. The destination host rearranges according to sequence number. In case of UDP, it cannot. Retransmission of lost packets can happen in TCP protocol. It means that any cumulative stream not acknowledged is retransmitted. It cannot happen in User Datagram Protocol because they don't wait until the acknowledge or acknowledgement. Error-free data transfer is actual in TCP protocol, whereas the UDP protocol does not check for the errors, and if the packet receives it and processes it by the lower layers of OSI reference model, it means that it considered that packet is completed. TCP can perform flow control. It means it can limit the rate a sender transfers data to guarantee reliable delivery. The receiver continually hints the sender on how much data can be received, controlled by the sliding window. When the receiving host's buffer fills, the next acknowledgement contains a 0 in the window size to stop transfer and allow the data in the buffer to be processed. And however, in UDP, user datagram protocol, it cannot be happened because the UDP is more simple protocol than a TCP. It do not have a flow control and generates packets which receiving from the application for the upper layers. TCP has a congestion control, whereas the UDP doesn't have. TCP uses the sequence number to identify each byte of data. The sequence number identifies the order of the bytes sent from each computer so that the data can be reconstructed in order, regardless of any fragmentation, disordering, or packet loss that may occur during transmission. For every payload byte transmitted, the sequence number must be incremented. In the first two steps of the three-way handshake, both computers exchange an initial sequence number, ISN. This number can be arbitrary and should in fact be unpredictable to defend against TCP sequence prediction attacks. TCP primarily uses a cumulative acknowledgment scheme where the receiver sends an acknowledgement signifying that the receiver has received all data preceding the acknowledged sequence number. The sender sets the sequence number field to the sequence number of the first payload byte in the segment's data field, and the receiver sends an acknowledgement specifying the sequence number of the next byte they expect to receive. For example, if a sending computer sends a packet containing 4 payload bytes with the sequence number field of 100, then the sequence numbers of the 4 payload bytes are 100, 101, 102, 103. When this packet arrives at the receiving computer, it would send back an acknowledgement number of 104, since that is the sequence number of the next byte it expects to receive in the next packet. In addition to cumulative acknowledgements, TCP receivers can also send selective acknowledgments to provide further information. If the sender infers that data has been lost in the network, it retransmits the data. Sequence numbers and acknowledgements cover discarding duplicate packets, retransmission of lost packets, and ordered data transfer. To assure correctness, a checksum field is included. The Tcp checksum is a weak check by modern standards. Data link layers with high bit error rates may require additional link error correction detection capabilities. The weak checksum is partially compensated for by the common use of CRC. It's a cyclic redundancy check or better integrity check at layer 2, below both TCP and IP, such as is used in PPP or point-to-point protocol or the Ethernet frame. However, this does not mean that the 16-bit TCP checksum is redundant. Remarkably, introduction of errors in packets between CRC-protected hops is common, but the end-to-end 16-bit TCP checksum catches most of these simple errors. This is the end-to-end principle at work. TCP uses an end-to-end flow control protocol to avoid having the sender send data too fast for the TCP receiver to receive and process it reliably. Having a mechanism for flow control is essential in an environment where machines of diverse network speeds communicate. For example, if a PC sends data to a smartphone that is slowly processing received data, the smartphone must regulate the data flow so as not to be overwhelmed. TCP uses a sliding window flow control protocol. In each TCP segment, the receiver specifies in the receive window field the amount of additionally received data that it is willing to buffer for the connection. The sending host can send only up to that amount of data before it must wait for an acknowledgement and window update from the receiving host. When a receiver advertises a window size of 0, the sender stops sending data and starts the persist timer. The persist timer is used to protect TCP from the deadlock situation that could arise if a subsequent window size update from the receiver is lost, and the sender cannot send more data until receiving a new window size update from the receiver. When the persist timer expires, the TCP sender attempts recovery by sending a small packet so that the receiver responds by sending another acknowledgement containing the new window size. If a receiver is processing incoming data in small increments, it may repeatedly advertise a small receive window. This is referred to as a silly window syndrome, since it is inefficient to send only a few bytes of data in TCP segment, given the relatively large overhead of the TCP header. TCP senders and receivers typically employ flow control logic to specifically avoid repeatedly sending small segments. The sender-side silly window syndrome avoidance logic is referred to as Nagel's algorithm. The final main aspect of TCP is congestion control. TCP uses a number of mechanisms to achieve high performance and avoid congestion collapse, where network performance can fall by several orders of magnitude. This mechanism controls the rate of data entering the network, keeping the data flow below the rate that would trigger collapse. They also yield an approximately maximum minimum fair allocation between flows. Acknowledgments for data sent or lack of acknowledgments are used by senders to enter network conditions between the TCP sender and receiver, coupled with timers. TCP senders and receivers can alter the behavior of the flow of data. This is more generally referred to as congestion control and/or network congestion avoidance. Modern implementations of TCP contain 4 intertwined algorithms. They are slow start, congestion avoidance, fast retransmit, and fast recovery. In addition, senders employ a retransmission timeout or RTO that is based on an estimated round-trip time or RTT between the sender and receiver, as well as the variance in this round-trip time. The behavior of this timer is specified in RFC 6298. There are subtleties in the elimination of RTT. For example, senders must be careful when calculating RTT samples for retransmitted packets. Typically, they use Karn's algorithm or TCP timestamps. These individual RTT samples are then averaged over time to create a smooth round-trip time, SRTT, using Jacobson's algorithm. The SRTT value is what is finally used as the round-trip time estimate. Enhancing TCP to reliably handle loss, minimize errors, manage congestion, and go fast in very high-speed environments are ongoing areas of research and standards deployment. As a result, there are a number of TCP congestion avoidance algorithm variations.